Hello, this video is an explanation of this 8-bit CPU I designed in Minecraft. The goal of this project was to design a CPU without looking up any existing designs. I did look up designs for individual components such as the memory controller units and the other bits and optimized several of those. But overall, I constructed the high-level architecture myself. And this, of course, has been done many times before, so it was just a challenge to myself to see if I could remember the necessary components to construct a working CPU. And it was a success. So this is an 8-bit CPU with 32 bytes of RAM, and it works with a Turing-complete instruction set. I'll break this into an overview of the components, and then I'll give a demo of it working at the end. The architecture of this system is fairly traditional. We have a long set of modules here, which are the random access memory modules. We have the control unit in the center, and we have the ALU, which is pretty much covered in this area right here. And I'll go over each of these components individually. I think first I'll start out with the random access memory modules, which are these squares. Here is a 4-byte unit, and then we have 8 of them, so that's the 32 bytes. These white rectangular borders are the modules that I designed individually so that I can clone them and duplicate them as needed. But of course, I designed really just individual slices here and then cloned them as well within a module. So it's just to give a high-level modularity to it. So we'll go over this RAM module very briefly. The core concept of this, or how it actually stores memory, is this little tiny bit of the circuit right here, which is basically just 2 repeaters. One of them locks the other, which creates a latch circuit effectively. And so as long as we wire up the control wire for this, the locking repeater, we can control when this one will lose or retain its signal, or effectively. So that's our way to remember things. So we can, when this is disabled, the signal passes through. When this is enabled, then the signal is locked in place and cannot change, either whether it's on or off at that point in time. So of course, from that knowledge, you can see that this line of redstone dust, which is basically a wire, is controlling the write enable capability, which comes down to this blue wire all the way down to here. So that's something to keep in mind. But basically the inputs we have are the write enable wire. We have the address that we're going to write to, which is fairly complicated. That's down here with these green lines. And because we have to decode, this is effectively a decoder here, all this logic that figures out which cell that we actually want to address is activated at a given time. And that's for writing to that memory and also reading from it. And then we have the other inputs and outputs are the data in lines and the data out lines. So the data in lines are going to be what we're going to store into the memory, and the data out lines are what we're reading from it. And those are in the red. The red is the outlines, I believe, yes, and the data inlines are the dark blue. Here you can see that we can read from this side or this side, but eventually it combines into one line right here. So there's and then here's where we can we can block off this line if we're actually reading from this side. So as a typical in computer architecture, there's a lot of redundancy here that could be potentially eliminated with a better design, but here we have a lot of wires that are only half of them are used at a given time. But this design overall is very, very inefficient in terms of duplication of gates and wires in space. But I was not designing it to be optimal, I was designing it just to be functional. So that's a pretty good overview of the RAM module. Now we can look at, let's see, the ALU. So the ALU is the Arithmetic Logic Unit, which does the actual computations on the data that we're going to be processing. And it starts pretty much, well, this component here and this component and this whole component here. So the most basic logic functions are implemented in this little submodule. We have, if we just look at the very top slice, because all these things are repeated basically vertically, we have 8 instances of the same logic function stacked on top of each other. So if we just look at the top layer, we have 1, 2, 3, 4, 5, 6, 7 functions basically. So I know these are functions because they take 2 inputs and they output 1 output. So in general, this ALU is operated on 2 data inputs. One of them is the accumulator, which is the register that stores your sort of working data value. And then your second value usually comes from memory. So we have a direct wiring of whatever's being read from memory at the current address that becomes the second input into the ALU. And that's really important because if we only have one value, the accumulator, which is stored somewhere in here, which we'll get to, if we only have one value, then we can't really compute much. We can only do unary functions, but with 2 values, we can do pretty much all the main mathematical operations that we need. So here we have some examples of some units. I'm not going to be able to go over all of these because I don't remember them all. I'd have to look up exactly which gates, but some of these gates are XOR and or. There's a NOT gate in here somewhere, but it's kind of hard to figure out which one is which until I look at all the signals and outputs. But these are very simple ones because they just combine, take 2 signals and create a third one using some logic gate. This is a logic gate here. This is another logic gate. These 2 are a little more complicated, and I do know that these are some form of adders or subtractors. These are probably adder, one adder and one subtractor. I think I didn't combine the 2 into a single unit because it was a little more complicated for the control logic. In a typical CPU, you would combine the adder subtractor or just reuse the same hardware because addition and subtraction is really the same operation, just where you negate the second input for subtraction before you feed it into the adder. But in this case, I think for simplicity, I just have 2 separate units so that I can wire out the opcodes of the instructions very straightforwardly. And I just duplicated the logic here. One of them is going to be negating one of the inputs. I don't know if we can see that somewhere here, but I don't know where it happens. It's going to be somewhere. In any case, these are the, going from the simplest logic gates into the more complicated ones. Adders are very complex in terms of how to lay them out. This is fairly compact design that I developed from several others in the sort of technical Minecraft literature. This one is this last big glob of units is actually one logic function, and that's multiplication, which is rather complicated. So you can get a very good idea of the complexity between an adder, which is this unit here, and a multiplier, which is this unit here. But the main logic of a multiplier is not much different from what you'd learn in grade school for multiplication, where you just do a bunch of sums and some carries and combine them all together. And you can kind of get an idea of that from this mess of wires here. But this is basically shifting various bits from one of the inputs to do the like the shift of you're shifting over the digits. In this case, the digits are bits, but you're shifting over the digits to do the additions, and then these are the additions that are basically reducing the result into the final output. So we don't have to go through all the details here, but that gives you an idea that we're basically shifting one of the numbers multiple times into different slots, and then we're adding them together with the first one, and we're collecting out the results, and that is the multiplication. So the basic design of the ALU, though, is that we take all of these functions are going to execute on every clock, but only one of them is going to get its output selected. So that's what all these redstone blocks and target blocks are basically the selectors of the output. And so whatever is enabled, like in this case, this thing is disabled because this honey block doesn't carry a signal, so it's like a disconnected circuit. But if we lower this whole thing by one block, which is what this piston mechanism does, it'll take the target block down to this block, which does carry through the signal. So whatever's coming in through here is going to be passed through this block and out through this wire here, and then repeated all the way over here and out to this line. And similar for these units, they all will be enabled individually. So that's what this whole mess of wires does. And at that point, we get our result output onto this blue line, and it is wired out here to go to wherever it needs to. In this case, it will go to, well, it can either go back around to the input side here, or it can go out to here to be written to memory. There's all these sort of additional knobs and things that I don't remember exactly what to do, but they're something to do with the carry bits and the control bits, things like that, that are used for conditional jumps, things like that. I think the only thing else to note is that we have this magenta line down here. And this is actually how I control the clock on this CPU. It's actually, we don't have a fixed clock rate where we say like every 5 seconds we increment the clock. Now, this is a very, very slow CPU, by the way. But we have a dynamic clock, or a variable clock cycle, which is timed by these circuits down here. This basically gives how much delay, or it controls the delay for the cycle, given how much delay we need for this computation. So the simple logic functions here only have a delay of like 1 tick here. This is a repeater that controls how many ticks or delay that you add in. So these are 1 tick logic functions, pretty fast. Here's a 3 tick logic function that has been set to 3 ticks. Here's a little more. We get down to the adders and subtractors, and those are quite a bit more. They're, let's see, we got 4, 8, 12, 16, 20 ticks of delay on each of those guys. And then we get to the multiplier, which is a massive amount of ticks, which I'm not going to count, but that's, multiple seconds worth of delay. Because we have to allow for the signal to propagate through that entire mess of logic gates. So this is kind of nice because in the early x86 days, you would get clock counts for each of the functions or your instructions. And this is kind of similar here, where I guess I wouldn't call these clock counts, but these are timings for the clock cycle that tells you how long each clock cycle will last. So it's a little strange having the clock be a variable, but it makes sense when you think about it for this design, because we don't really need to have a clock at a fixed rate necessarily, although it is probably more efficient to do it that way. This is perfectly fine, reasonable to have a variable clock cycle length. And so that signal, again, is the purple or magenta wire line, gets down to here, and this is actually our clock line. So here we get down to the final clock line, and I believe this amount of delay here is for the memory controller to write, and so this is kind of a fixed delay. It's probably for the memory controller and the control unit to decide the next instruction. So there's our loop of our clock. This feeds into our control unit, which is our last component to get to, and it's definitely the most complicated and the most messy. These units, especially the RAM unit, is the most organized and consistent, because it's basically the same thing over and over again. There's not much variation. The ALU also is fairly organized, but it has various functions that it needs to implement, so they have various complexities and layouts, but their overall design is pretty much the same, where you take the two inputs and do something, and you get an output with the variable clock cycle length. Whereas the control unit has pretty much no pattern whatsoever. It's tying everything together, and there are many functions it's implementing, and they all require different logic. And I designed it last. I basically glued this unit and this unit together with this mess, so it's going to be the messiest in terms of layout, because I did not design it beforehand. I just kind of gave myself some space and assumed it would be enough space, which it was, but I did not plan out the layout at all, so it turned out into the spaghetti. Most of the control logic is in this bottom layer here, which is wiring all the signals together. I'm not going to go over each one, but each one is critical. If you remove one piece of dust, the whole machine will break. It's one of those things where debugging this mess is extremely difficult. We have to build up knowledge of each piece, which at this point I don't have that knowledge anymore. I've forgotten it in 4 years. But to gain it again, I'd have to go through a clock cycle multiple times, and I could derive what each piece is doing. I did start documenting a few things about what the input signals are, but that's as far as I got. In any case, this stuff down here is essentially routing signals to control when things happen in what order during an instruction cycle, which is fairly complicated. This part here is really one of the most important parts of the control unit, which is the accumulator register. I believe that is here or here. Well, you can see there's two memory units here, one here and one here. I forget which one is which, but I think this is the accumulator here. And this one may be the address register. So we have another register for the program counter, essentially, to know where we're reading from memory for the next instruction. So we definitely have to have two registers, essentially. And I think those are the two there. And so that, the rest of it is that we have a fixed function to increment the program counter. I pretty sure this is the program counter because it makes sense to be in a loop here, where I think it's incremented in this one of these circuits here, so that by default we will execute memory addresses one after another, basically sequentially, unless we get to a jump instruction, either conditional or unconditional, which will redirect our program counter to another location in memory. And this is what this logic does. It'll, by default, increment, well, it will always increment, but it'll use the incremented program counter or a new address coming in from the instruction, the previous instruction, to figure out where the next instruction will be read from. And that's what this is essentially for. And other than that, we have the accumulator part is basically just keeping track of a temporary piece of memory or temporary piece of data for our first input into our ALU. So that is used to basically, keep track of a loop counter, keep track of the indirect memory address for those instructions, various functions like that. It's basically a temporary buffer, effectively. A placeholder while we're working with some other piece of memory. We have the placeholder accumulator to do that. And here we have another kind of decoder, I believe. Well, I think it's actually just a mechanism to get it's part of the decoder to feed the address lines into the RAM unit. But that's coming in from the program counter control unit. So that's what's reading off this memory here. So this is actually something specific to this architecture that I've used here, is that the instructions are always 2 bytes in length. It's a fixed instruction width. And the first byte is basically the opcode that determines which ALU operation will enable. And the second byte is the instruction-dependent data associated with it. So for example, an add instruction can take the accumulator plus the memory address for the second operand to read from, and then it will write back to the accumulator, and then etc. So that second data byte is to give the instruction some sort of dynamic input. It can be a literal value, it could be a memory address, it could be anything. So I'll go over the instructions, or a couple of them, for examples, in a bit. But with that architecture, we have this memory unit that has 32 bytes, but we've organized it so that the even bytes are going to be the opcodes and the odd bytes are going to be the data parameters. And that's somewhat arbitrary, but oftentimes architectures will decide an alignment for instruction memory, which is what this is basically doing. And so all of our instructions are aligned on a 2-byte boundary, such that the even bytes are always the opcode and the odd bytes are the data part. So what that allows us to do is we can basically hardwire the setup of our control unit so that we know that we're going to be reading from this side the odd bytes or whatever it is for the opcode, and this side for the data. So it allows us to simplify some things about how we decode instructions, because we can get essentially both values at the same time. Remember I said that we read both sides of this memory controller, but we only get one value when we merge them right here at this junction. But that means that when we have both values available, we can switch between them very quickly. And so when we get the opcode, we can buffer it or let it pass through into the ALU and then switch to the other side of it and get the data value to do the next that operation immediately. So it's somewhat of a typical optimization where you do two things at once in parallel. You read the odd side and the even side at the same time, and then you have a opportunity to use both of those values without doing a whole nother read cycle. And this is used all over the place in computer architecture, where you try not to waste cycles that are already being done for you or doing some work for you in some manner. So this relies on that even odd assumption. If you didn't have that assumption, you would have to do that operation serially. Otherwise, I think this control unit is a bit out of reach for me to explain because I don't remember enough of it. But I think this gets to a good point of showing how this actually works. So I have documented these control inputs here, and these are all just manual buttons and levers pretty much down here at this position. I didn't really design a console so that the user can have everything in one place, but we just have to fly around and click on these levers and stuff. We have basically only a few functions here. I guess the main one is this button here, which starts the clock. So clicking this will basically start running the machine. But we're not quite ready for that because I want to explain the rest of the configuration knobs we have. We have this orange line here, which is basically an override to be able to program the machine before we start running it. So if we enable it here, we enter into this override mode, which I'll explain a little bit. I called it the override and reset mode. So it also resets the machine so that it will start at memory location 0 to start executing. So that's basically our reset line plus when we keep it enabled, it allows us to program the machine. So programming the machine is fairly straightforward. We have this giant 32 bytes of memory. It's a huge amount, of course. But we need to be able to set the values at individual cells. So that's what these knobs here allows us to override the address line for which cell we're going to program. So right now they're all off, so we're reading and programming memory address 0. I think I've documented here. This is the first bit, here's the second bit, all the way down to bit 7 or the 8th bit. So we have that address line. We also have this line of lamps over here, which is basically just reading off this red output line, which is basically just a way to show what the current value of the memory cell is. So in this one, I think it's the opposite of that one. Unfortunately, it's not consistent, but this is bit 0 and this is bit 7 at the top, so it's inverted. So this one, we can read it off from here. It's bit 0, 1, 2, 3. So that value here is a 8. It's a bit 3 enabled in an 8-bit value. Results in a value of 8. So what we can tell from this is that at memory address 0, the value stored in the memory is value 8, which can be interpreted however we want. This lamp here, I think, is showing the accumulator, which is just the copying over whatever's being read from the memory at the moment. So you can ignore that one. Okay, and the last bit of how we control this thing is that we have this input here, which is again the write data input into the memory controller. So this is how we're going to program values that we want into the memory. So this one, let's see, it's going from the bottom 0. Bottom is 0 and the top is the bit 7. So it matches the output here. So if, say, we want to program byte 0 to be, let's say, instead of 8, we'll do 12. So we'll enable bits 2 and 3. So we have that programmed here, but that does not do anything. It doesn't change the memory cell. But we have this button here, which is the write enable override, which typically this Scion line comes in and enables the write when we do a store instruction. But in this mode, we can override it like that, and that will propagate all the signals to write our input override value, 12, into the memory. So there we go. We got our 12 at memory location 0. But I'm going to write it back to 8, because if we leave it at 12, that would mess up our program. All right, so I'm going to write it back to 8. And there we go. It's stored. So with this mechanism, we can program our 32 bytes to be whatever values we want. And the values that we want are going to be our program that we're going to execute and any input data that we need for that program. So this is where I can start explaining the actual instruction opcodes and the program that we've written here. The program I've already written into this computer is Factorial, the Factorial mathematical function. It required, I believe, 14 or 16 bytes, maybe a little more, of memory. And so we can look through a couple of these bytes. We saw that the first byte was 8. Then we can look at the second byte by flipping this to get memory address 1. And at memory address 1, we have value 1. So far we have memory address 0 is 8, memory address 1 is 1. So that gives us our first full complete instruction. And then we can get back to that. But that's something to keep in mind. And then we can go to address 2. And what is that? That is, well, it's one more bit higher than 8, so that's 16. So we have a value of 16 at memory address 2. And the memory address 3 is, let's see, one bit higher than that, so that's 32. So we have 16, 32 there. So we go along that and we can read out what we have in memory. But that's a good point to explain what program or how the program is encoded. All right, so here I'm going to describe some of the instruction set of this computer, which I designed myself, but it's a very simple sort of RISC style architecture. And here I documented some of the semantics of the instructions, although I'm not sure if this is exactly what I ended up with. This is sort of my prototype. But as I described, each instruction is 2 bytes. And so you have your opcode and then you have your argument byte to be able to use for whatever. So for instance, the load arg could either be loading the accumulator with the literal value, or it could be loading the accumulator with a RAM, the RAM data at the arg's address, or the address specified by the argument. And similar for the store, you're going to be storing at the address specified by the argument the accumulator into that cell. And this is like prototyping some other indirect stores that I don't think I implemented, but I basically implemented the simplest possible primitive opcodes that I could. I also distinguished between direct and indirect instructions. Direct instructions treat the arg as the literal value, and indirect ones treat that as the address to read from memory. So I have one bit in the opcode selects between those two different modes. And then to be Turing complete, you also need some sort of control flow instructions. Jump is important for jumping to a address unconditionally, and you also need a conditional jump, such as jumps when the accumulator is 0, or jump when the accumulator is not 0. So I have at least those two. For example, terminating loops or looping or jumping to the beginning of a loop. Now I'll describe how I programmed Factorial into the machine, starting from a high-level piece of code. This is C code or whatnot, which has nothing to do with the machine, but it's how I wrote out the program initially, and then translated manually down into the more machine-level code pieces. So we start out with a high-level structured programming. In other words, C code. We have two variables declared. One is our input n, and res is our result. So it's going to start at 1 as the output, and then we're going to loop over. Basically, I goes from 1 to n, loop n times, and multiply a result by I. That's our factorial implementation. Very, very simple, imperative implementation of Factorial. Our first step of compiling this code is to convert it from structured programming, which is loops and recursion, for instance, to unstructured programming, which just uses conditionals and goto. And goto is typically seen in the C and C++ world as very dangerous because it's harder to follow the control flow. I don't think this is necessarily true, depending on what it's used for cleaning up resources or whatnot. But in any case, it's less used, and for good reasons. But when we're writing assembly, or we're targeting assembly code and code generation, goto is an absolute critical concept to understand, because that's what essentially all our machine can do at the low level, is a goto, which is a jump. So to translate from the loop to goto, it's fairly straightforward. We just have to split up our pieces of our loop condition into an appropriate set of steps for goto. So in this case, we're going to actually reverse the loop. We're going to go from n to 0. And this is a typical technique for compiling, since we already have our value at n and we only have a instruction to compare against 0. We're going to count down to 0 to determine when we're going to finish. So starting from n going down to 0 is equivalent from starting from 1 and going up to n. Right? As long as we get the number of loop iterations correct. So in this case, we'll execute this part n times. That's why we want the condition to be first, because we don't want to execute the loop on the last step, or on the step when I equals 0. So we execute, or we jump to done when I equals 0, which basically ends the program. And this is basically our halt condition. But if it is not 0, we're going to continue on, do one step of the loop, result times equals I, subtract 1 from I, and then go back to the start of the loop and try again. This is a fairly simple translation from this step to step. So understand that we're reversing the loop order, and we're translating the conditions into gotos, or the loop conditions into this is a unconditional jump. This is a conditional jump. All right, so now we're going to convert this into symbolic assembly. Symbolic assembly, we still have variables, variable names to make things clear. We don't have high-level ifs and go-tos. We have low-level instructions, load, stores, and jumps, and arithmetic operations. So, but it's fairly straightforward to translate. Here, we also have to now translate into our accumulator model and figure out how we're going to allocate registers. Essentially, we only have one register here, so we have to store things in memory. Sometimes we can use the accumulator. So this is a little bit more involved step. In this case, we're gonna use the accumulator to prepare what we're gonna store into RAM at this address, the result address. So remember, we wanted to initialize our result to 1. Well, we can't actually store 1 directly into result because we only have 1 byte for our store instruction. We don't have 2 bytes to say here's the address and here's the value. So the only way we're going to get our value of 1 is by loading it into the accumulator first. So this is a direct load, meaning that this is a literal value. We're not reading from memory. We're just setting the accumulator to 1. Then we can store that value from the accumulator into the result memory cell. And again, here results is not fixed at a location yet. We're just saying some location in RAM will be the result. Now, load has 2 forms because we can either use the direct form, where we load a literal, or we use the star to indicate indirect, meaning load not n into the accumulator, but the value at location n. And that's what this does. So we load n into the data at location n into the accumulator. And so n was our input, the address of our input value. It's not the value itself. So here, this is the same. This is what we did with the jump. We have a loop. We still have labels for loops. We still have labels for jump targets. So this is going to be the address of the instruction eventually. And we have multiply, we have store, we have load, blah, 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 because the rest of it is fairly straightforward. All right, then we go from symbolic assembly to raw assembly. Raw assembly, we remove a lot of the human readable sugar. So I left the comments here just so that you can see it's really the same thing. But now we're going to fix all of our addresses. We're basically linking everything together now. We have our result at hex 20 and our input at hex 21. So that's value 32 and 33, which are described in the demonstration. So what do we have here? We have now we basically just replace our symbolic labels with our fixed addresses that we've chosen. Otherwise, it's the same. For the jump targets, we now have to know the address of the individual instructions, which we've written out here on this left side. So we have, for instance, the done is at the end, which is 14, which is our halt. So our jump zero here has the argument for hex 14. All right, and the last step is to encode this assembly into machine code. And that requires us to know the values of the opcodes for each of the instructions. And that's what this table gives. It's a subset of the instructions, but it's the ones that we've used. And this is very, very straightforward. We just take our assembly code and we convert it into, we convert the opcode and we leave the data value basically the same. So our load instruction is load direct is 08. So we're going to do 0x08. And that 0x01 is our data value, data argument value. Same thing for store. Our store is hex 10. So we're going to use hex 10 and then hex 02 or hex 20. And we do the same thing for every line here, and we'll get a table of all of our program data values. And this is exactly what we're going to write into our memory. Starting at address 0, we're going to write these bytes 2 at a time or 1 at a time, but in these pairs, opcode, op argument, until we get to the end. And then we also have to keep in mind our result values at hex 20 and our inputs at hex 21. So we have to write our input at this location, and we'll expect our output in this location. And that's pretty much it. All right, so we have here our input program. Let's do factorial 5. So we're going to go to address 33, which is our input. And what do we have? Currently it's 0, so that's not going to do anything. We want to program a 5 in here. So we need bit 1, and we need bit 4, or yeah, bit 2 to get a 4. And that should be a 5. And we're going to write that out to memory. Alrighty. Make sure that stuck. Good. Make sure to disable the overrides, otherwise we will be corrupting our data as we execute the program. Alrighty. So it's important to disable the address lines before we start execution, because otherwise we will also corrupt the address lines, which will mess everything up. All right, so let's start this program now. If we disable this override mode, we will see that the address line shows a 1. Well, what that actually means is that it's address line 1, but it's actually reading 0 and 1. So it's showing the odd address, but it's basically ready to read from address 0 and 1. That's just a artifact of how the dual read input is designed. Remember, I said that it would read the even byte and the odd byte at the same time, and then use the even one for the opcode. So it's showing address 1, but you can interpret that as 0 and 1. Now, to start executing this machine, we would hit this button here, which would start out the machine and run until it hits a halt instruction. However, we can also enable this mode here, which is a single step mode. So it's kind of like a debug mode, where when we click on this button, it will only execute one instruction at a time, and it will halt after each one. So we can use this to kind of step through and show a couple example instructions, and then we can disable that and continue until it finishes. So let's start with the first instruction. We're going to click on it, and let's see, what does this do? So now we're at address 3, which again is address 2 and 3 for the next instruction. But what is the current state of the program? Well, I don't know. All right, let's continue running the program. All right, so the program is running, and we can read off the address lines as they are being modified, but it's going to be kind of hard to interpret what exactly it's doing because this address line is for both the instructions and for the data that's being read. So it's alternating between data reads and instruction reads. But we can kind of keep track of the accumulator here and see kind of what it's doing. Here's the output of the memory controller, which is also alternating between data reads and opcode reads. So it's going to be kind of hard to interpret without pausing. But we can see the accumulator updating every once in a while. And we can go over here into the arithmetic unit. That can give us an idea of what's going on. So here you saw this one going up and down. That means that function was being executed. Well, there was a multiply that just happened. Or actually, it's enabled right now. Here you can see it's enabled, and eventually that output, yeah. So now the output is locked. And then if we go down to the control, the timing circuit down here, we can get another idea of what's going on. Let's see if we can catch one of these guys. Oh, there we go. There was an add that just happened. An add or a subtract of some sort. See if we can capture the multiplier timer. There should be one coming through at some point because we're doing factorial. We're multiplying things in a loop essentially. So here we go. Here's a multiply. You can see the timer is going through its circuit, and once it finishes, that output line goes all the way here. And you can see it's already on the next loop. There we go. So that's basically what's going on. Let's see. We're expecting the result value to be 120. That's what factorial 5 should be. So let's try to find the output 120. It is not a fast machine, but it's essentially an emulator for an 8-bit CPU. And emulator is notoriously slow. And this is a very cool application of emulation, since we can visually see what's going on in a three-dimensional navigatable setting, which I think is very cool conceptually. So I think our machine is finished. Where did it finish? It finished at this address, which is, let's see, it's an odd address. Well, that is value 16 plus 4 plus 2. So that's 20, 22. 22 and 23. I believe that is the finishing address. If we look at our program, yeah, that is the finishing address. So at the end of the program, remember we inputted our value in memory address 33, decimal 33. Our output address is 32. And those were arbitrary, but those are just the addresses we picked when we generated our machine code. So to read back our value, we're going to enter into reset mode. Remember, that's going to reset the machine, but it will not reset any of the memory locations. So that preserves all of our values stored in memory. So I'm going to reset our machine, and then we're going to read back our value at memory location 33, or 32 is our output. So 32 would be this, yeah, bit 5 address enabled. Let's see what value we have at address 32. We have, well, hexadecimal 78. hexadecimal 78 is value 120. So we got our expected result of factorial 5. If we look at our memory address 33, which again was our input, which was 5, we'll see that it is 0. And why is that? Well, we used that input location to count down from 5 down to 0. Basically, it was our loop counter address or memory cell. So we get our expected value of 0. That terminated the loop and finished the program. So that basically sums up the high-level functioning of this machine. I hope you learned something, and thanks for watching.